I'm going to talk about constant voltage sources. When we're dealing with theorems such as Thevenin and Norton, we deal with circuit analysis techniques where we apply a constant voltage or a constant current source. For Thevenin's technique, or for Thevenin's law, we use a constant voltage source. And we're going to explore, initially, a practical voltage source. So the function of a voltage source is to deliver a known voltage to a circuit. And in diagrammatic terms, or schematic terms rather, we express that as a voltage generator, which is what this sort of circle is here, with a voltage and an arrow pointing across it. So that is going to be a voltage generator, and that is in series with some sort of internal resistance, okay, a resistor referred to as Rint, and the voltage source, well, it represents the magnitude of the voltage supplied. The resistor, or the internal resistor, represents the internal resistance of the source itself. So for a voltage source, the value of Rint should be as low as possible. Okay. So if we consider the diagram that we have here in front of us, we've got this diagram that shows two conditions: no load condition and load condition. So this is classed as a practical voltage source, the kind of thing you'd actually see in real life. Now, if you've got no current flowing, then you know that your voltage is going to be equal to V0, and I'll probably demonstrate this later on, but well, you will see this later on when we look at ideal. Okay, but when we have a current flow in a circuit, so we've now connected up a load, RL, because that's kind of the reason why we do this, we connect things up to make them work. So when a current flows, there must be a voltage drop across this internal resistance. Okay, obviously there's going to be a voltage drop across RL, that's going to be the output voltage, V out, but there's also going to be a voltage drop across Rint. So under no load conditions, we'll end up with this situation. I'm going to move this over because it's maybe a wee bit confusing. So under no load conditions, you get V equals V0, or V out rather. However, under load conditions, we will land up with the output voltage is going to be the supply voltage minus I times Rint. Okay, so this is just the application of Kirchhoff's voltage law here. So under load conditions, the value of the output voltage will depend on the value of the load resistor, and it will always be less than the supply voltage itself. So let's now take a look at an ideal voltage source. You can see here that now what we've done is we have removed the internal resistor. The reason for that is because we've assumed that it's going to be 0. In other words, if Rint is 0, then we can replace that with a short circuit. That's why we call this ideal voltage source. Now in practicality, that's not actually the case. Otherwise, our mobile devices and any devices that are rechargeable with a set of cells, they wouldn't heat up as a result of being used or even charged. So the ideal situation really only applies to theoretical conditions, etc. So for an ideal voltage source, the internal resistance of a voltage source should be as low as possible. Under our conditions, from a theoretical perspective, we're going to consider that to be 0. So we'll end up with this condition here. Under no load conditions and load conditions, we'll end up with the same state. So in this case, you can see that the value of our output voltage will always be the same, irrespective of what the load resistance will be. So the source therefore supplies a constant voltage for any load condition, and we call that a constant voltage source. And I like to write this out as CVS, being constant voltage source, obviously. Let's now take a look at a small example that demonstrates this practice. We have two situations that both have a voltage source set to 10 volts, but the resistances, in other words RL, are 10 ohms and 5 ohms respectively. And when we apply these to our equations below, we can see, obviously from Ohm's law, that it's the current that changes. So as the load changes, the current supplied by the CVS, the constant voltage source, it changes, but the output voltage remains constant. So your CVS is basically defined as a device that will supply a constant voltage to a circuit irrespective of the load connected across it.